Hello everyone. In this video we will discuss about conics. Conics are two-dimensional curves which are formed when a plane intersects this double napped cone. So each time a plane intersects in a different way, we get one of these shapes called as circle, parabola, ellipse and hyperbola. And straight lines is a degenerate case, which we will also see in this video. So let us see how these shapes are formed. As you can see here, this is a cone, and when a plane intersects this cone, we can see the formation of a circle, ellipse, parabola and hyperbola. So the general equation of a conic looks something as follows: ax square plus bxy cy square dx plus ey plus f. And in order to form a particular form of a curve, it need to satisfy certain properties. So we will be seeing both necessary conditions and the sufficient conditions for each of these above mentioned conics. So let's first start with the degenerate case, which is a line. Line is actually not a conic, but it is a degenerate one. Whenever the conics are not able to form the proper shape, we actually get a line or a point or something else. So that we will see shortly. But what are the conditions for the line? If a, b and c, all three terms are zeros, and if d and e satisfy this property, d square plus e square not equal to 0, then it forms a line. So we know the basic equation of a line, whether it is ax plus by plus c equal to 0 or y equal to mx plus c. They represent the general equation of a line. So this particular general equation also forms a line when a, b and c are equal to 0, and any one of the quotient, either d or e, should be non-zero. To enforce that, we are using this d square plus c square not equal to 0. So then this is one form of a line passing through an origin, but the line can be anything in a two-dimensional coordinate system. And this forms the necessary and sufficient condition for a line. So this is one example of a line. So let us see one other conic, which is a circle. So circle, the necessary and the conditions for a particular general equation to be a circle is as follows, where the quotients of a and c should be same, and the b term, the cross term, should be equal to 0. And this is the necessary condition, but we also have sufficient conditions, which we'll see soon. Then we have ellipse, and we know this circle is actually a special case of ellipse. So the general equation of ellipse looks as follows, and the necessary conditions for a general equation to be a ellipse is b square minus 4ac less than 0. So, and for the parabola, the condition would be b square minus 4ac equal to 0, and this is how two different forms of parabolas will look like. And for hyperbola, these are the conditions where b square minus 4ac should be greater than 0, and the signs of a and usually c will be opposite in the case of hyperbola. So this is how conics are formed and their examples, but these are only the necessary conditions. Now let us see what are the sufficient conditions it need to satisfy in order to become a perfect conic. So first we have something called as degeneracy check. Let's take this general equation. When you represent this in the form of a matrix, it would be something as follows. So if you multiply this and equate it to 0, you will get back this general equation. So now take this matrix, and if we compute the determinant of this matrix, and if this determinant is equal to 0, then we call it as a degenerate conic. And if the determinant is not equal to 0, then we say it as non-degenerate conic. So only when the conic determinant, the delta, is not equal to 0, or when it is a non-degenerate conic, we get a perfect shape for a circle, ellipse, hyperbola and parabola. If delta is equal to 0, then it will be a degenerate conic, which means it will condense to either a line or a point or an imaginary shape. So this condition determines whether it will form a proper conic or not. So, and what is the intuition? The intuition is this matrix delta is the determinant equal to 0 means that it is not a full rank matrix, and when it is not full rank, this particular whole expression can be decomposed into two linear factors, and therefore it no more becomes a conic but condenses to a line. So these are the sufficient conditions. So apart from b square minus 4ac equal to 0, the delta should be not equal to 0, only then we get the parabola. And for b square minus 4ac greater than 0 and delta not equal to 0 gives us hyperbola. And for ellipse, b square minus 4ac should be less than 0 and delta should not equal to be 0, and a and c must have the same sign. So these are the conditions for ellipse. And circle is just a special case of ellipse, where a equal to c and they both should not be equal to 0, and b should be equal to 0 and delta should not be equal to 0. So basically delta, this determinant not equal to 0, is going to determine whether a conic is going to form or not. So let's see more details of what is the importance of this delta. So this is how we can define the degeneracy. A conic is degenerate if it does not represent a proper 2D curve but instead reduces to one of this form: a pair of lines, a single line, a single point, or no real graph. Sometimes we have an equation but we can't visualize it because it is no more a conic. So that situation also we encounter. So let's see more details. So this is our general equation: delta equal to 0 is a degenerate conic, and will have a proper conic, for example ellipse, parabola, hyperbola, when delta is not equal to 0, and we will have a degenerate conic when delta is equal to 0. So let's see more details about it. Let's take one example where delta is equal to all ones. So this is of rank 1, so definitely delta is equal to 0, so it will form a degenerate cone. So let's see how the equations would look like. So this is the equation when you multiply x, y, 1 to the both sides and represent. This is the quadratic form which we get, but when you simplify this we get as follows. And when you substitute t is equal to x plus y, you get this, and t plus 1 whole square is equal to 0, which means that x plus y plus 1 whole square equal to 0. So this does not represent any proper conic. It is actually a line with two coincidental repeated lines. The same line it is getting repeated here. So this is happening. The second order general equation has condensed to a line because this matrix is not full rank, and also the determinant is equal to 0. So in order to have a proper conic, the determinant should not be equal to 0. So let's take few more examples. For example, if you take this, the signs are opposite, we could possibly think that it is an hyperbola, but it is not a hyperbola. When you decompose it, you get two lines, intersecting lines, and this kind of looks like a second order equation, but this decomposes to two lines, parallel lines, and x square plus y square, the signs are same, and it looks like a circle equation, but this condenses to a point. And this x square plus y square plus 1 is equal to 0. This does not have any real solution, and therefore it's an imaginary ellipse. So in this way the conics will become degenerate when the delta is equal to 0. So let's see the same idea here. So this is what is our general equation and its matrix representation. This is the delta, and important thing is this delta matrix has certain very good properties. If you see it, first of all, it is a symmetric matrix, and we know for every symmetric matrix, for every real symmetric matrix, we can have a orthogonal eigenvectors, and we can in fact orthonormal eigenvectors, and we can construct the eigenvector matrix with completely orthonormal eigenvectors as columns, and we can do an eigenvalue decomposition as q lambda q transpose, where q is an orthogonal matrix with orthonormal column vectors. So this delta will be a diagonal matrix with eigenvalues occupied in the diagonal positions. So there is a very good linear algebra interpretation when you decompose this delta into q lambda q transpose. Let us see that. So and the important thing is the shape of the conic is decided not by the DEF, but it is determined by this first quadratic terms, ax square plus bxy plus cy square. So we will only be taking this and analyzing it. So when you represent in the form of matrix, we get something as follows, where M is this intermediate matrix and it's a symmetric matrix. Therefore we can have a real we can have an orthonormal eigenvectors, and when you do eigenvalue decomposition, this is what we get it, where delta 2 has eigenvalues in the diagonal position, and these eigenvalues are going to actually determine which shape it would be. So if lambda 1 equal to lambda 2 and if they are both greater than 0, or if both of them are less than 0, which means that having the same sign, then it will form a circle. And if lambda 1 is equal to lambda 1 and lambda 2 are greater than 0 or both less than 0, but they are not equal, then it will get an ellipse. If both are greater than, if they have an opposite sign, we get a hyperbola. And if the lambda values are, one of them is equal to 0, then we get a parabola. So these are the conditions when we will be having what conic. So eigenvalues are going to determine what form of conic we are going to get. And why is it happening? We will see the intuition behind it. So if you see this second order term, ax square plus bxy plus cy square, when you represent the same thing in the form of a using eigenvalue decomposition, this is what we get it. And this particular component q2 transpose xy, or the corresponding transpose term, these are nothing but a rotation term. So this is actually a rotation of this particular vector. So when you rotate it, you get a new vector, and the same transpose is written here. So in a way, what is happening is this whole coordinate system is actually getting rotated, and the equation is getting condensed to this form. So this xy term can be easily eliminated just by rotating the coordinate system and representing in this new coordinate axis x dash and y dash. So we have these two terms, lambda 1 x dash square plus lambda 2 y dash square, and therefore now lambda 1 and lambda 2 is going to determine what shape it is. This b term is not going to determine or this xy term, but we have these new terms lambda 1 and lambda 2 which are going to determine the new shape. It's important to note that these lambda values are confined to this matrix, and it is not related to the degeneracy matrix, because here when lambda values are zeros for the 2 cross 2 matrix, we are getting parabola. But we have seen earlier that when the determinant of the degeneracy matrix is 0, it becomes a degenerate, so it will not form a conic. But you have to note, we have to remember that the eigenvalues of this 2 cross 2 matrix are not same as the eigenvalues of the degenerate matrix which we have seen earlier. So this representation is basically used to show that these values of eigenvalues can determine the shape of the conic, and also it also lets us know that this cross term is just can be avoided by properly rotating the coordinate system. So, but in order to have a thorough check whether the curve, the general equation forms a degenerate or not degenerate, that can only be checked by the matrix which we have seen earlier, which is by computing the determinant of the matrix, and thereby checking whether it is equal to 0 or not equal to 0. If it is equal to 0, then it will be a degenerate cone. If it is not equal to 0, then it will be a non-degenerate cone, which will lead to one of these shapes. So that's the core idea, and this idea can be extended for higher dimensions also. Till now we have seen 2 dimension x and y. If we extend for 3 dimensions, we get surfaces like planes, paraboloids, spheres and ellipsoids, whose general equation looks like this, and whose shapes would look like this. So this is a plane in x, y and z, paraboloid, ellipsoid and sphere. So if at all, if we extend the same idea to the n dimension, the equation, the surfaces will become hypersurfaces, which are called as hyperplane, hypersphere and hyperellipsoid, and the general equation will look like this: x transpose qx plus p transpose x plus r equal to 0. So each of these particular equation or the earlier equation are actually the special cases of this equation. When the x vector has only 2 dimension, it becomes a conic. When x vector has 3 dimension, it becomes surfaces, and when it is more than 3, it becomes hypersurfaces. So the degeneracy check is also same. If the Q matrix determinant is equal to 0, then it is degenerate, which means that it condenses to lines or points. And if Q matrix has a non-zero determinant, then it would be a non-degenerate, and therefore it can form various shapes. In 2 dimension it forms circles, ellipse, hyperbola, and in 3 dimensions it forms the corresponding surfaces which are mentioned here. So this is the summary of all 2-dimensional quadric equations and their corresponding geometry, and when they would form conics, and when how to check the degeneracy. So this is the summary of the everything. Thank you.